Hi everyone, welcome back to Surviving Math with Shan. You're here with Shani Harris, and this is differentiation part 2. Yeah, so here we are. We'll be covering these concepts. So the first one, we have first order linear estimates. We're moving on to higher derivatives, then concavity and points of inflection, stationary points, and finally increasing and decreasing functions. Although this is part two to differentiation, please note that I haven't included all concepts. For example, implicit differentiation, as well as the equation to a tangent, the equation of a tangent to a curve. So I'll be posting a video separately on those concepts at a later date. This is what we have today. This is what we'll be looking at, and let's just get into the video. So here we have first order linear estimates. When do we use this? So this concept is used when we have a function that may be too difficult to work with directly. So instead of using that function to determine some value, we're determining some simpler function that would give us an estimate. So whatever value we substitute in it, we're going to get an estimate. And this simpler function, we would have to determine it based on given information. And you're going to see how that comes into play. So here we have our first order linear estimate general equation. So we're seeing that in order to determine that simpler function, we would have f of x naught plus f prime of x naught times x minus x naught. And this is the first order estimate of f for x near x naught. So you might be thinking, where x and x naught come into play? What's going on? Here we have our graph. And we have this curve, and we have the tangent touching the curve at one point, because it's a tangent. The point that tangent is touching the curve at is x naught and f of x naught. That's the coordinates. If we want to consider some x value that is really close to x naught, let's call that x. And in fact, it should be closer. Hold on. Some x value that is really close to x naught. Like it's right here, basically. All we're seeing is that since the tangent touches the curve, at this point, x naught and f of x naught, that's the coordinates, and we're considering an x that is close to x naught, meaning that since the tangent touches the graph at that point, if you look right here, there's some space. There's this little space. And if you think about the whole idea of approximation, we're just considering some close values. So if we have 1, right? We have 1.1. What is a value close to 1.1? 1.12, 1.13, values like that. So we're saying that since if we consider x that is close to x naught, in the same vicinity, basically, we can find some approximation. So this whole idea, this general equation, is basically us using the equation of a tangent to a curve, as well as other ideas. So just to add more clarity, we have a function. This is our curve. So the function of the curve, basically. And we want to find what value that function is going to give us when we substitute x naught into it, right? So we're finding what is f of x naught. Since we have a tangent that touches the curve at that point, all we're saying is that we can, at this point, basically, the equation of the tangent would basically give us the same exact value. Why? Because the tangent is touching the curve at that point. However, if we're supposed to consider x values that is in the same vicinity right here, where the tangent is not touching the curve at that point, is touching the curve at this point, however, it's close, we're going to get an approximation with the x values that are close to the point, the x that the tangent is touching the curve at, basically. which is why we're up here, we're saying is that this works when x is near to x naught. So it has to be in the same vicinity. So here's 5 steps you can follow to determine the first order linear estimates. And our first one is to put what you already know in the general equation. And usually this is the first step with a lot of mathematical problems. So whatever information that you're given, you're just going to put it in the general equation. Our second step is to substitute the value of x naught into f. And when you substitute the value of x naught into f, the given function, you're just going to find f of x naught. So you want to find that value. Our third step is to differentiate the given function f to find the first derivative, f prime. And after doing that, you should substitute the value of x naught into f prime, the first derivative of the function, to find what is f prime of x naught. And our final step is to put all results in the equation. And that's how you get the first order estimate. So here's our first example. Determine the equation of the tangent to the graph of f of x equal cube root of x at the point 8 f of 8. Also, find the first order estimate of a cube root of 8.05. So here we have our question. And we highlighted what we already know. So the question gave us the function. The function is f of x equal cube root of x. And we also know the point that we're considering, which is this coordinates, 8 f of 8, right? So we're going to put what we know basically in the general equation. So because we want to find a simpler function that's going to give us approximation for this. So we know that x naught, let's say this, we know that x naught is 8 from the coordinates because that's the point where basically the tangent is touching the graph, the curve. But yeah, so we have f of 8 plus, we don't know what is f prime, we're going to find that out. So f prime of 8 times x minus 8. So that's our first step done. Next, we want to find what is f of 8. We're going to go to our second step. Substitute x naught into f, the function. So we want to find what is f of 8. So we're going to just substitute normal. So where was the x right here? We're going to put 8. And the cube root of 8 is simply 2. Next, our third step, right, is to basically differentiate the function we're given. So this is our given function, f of x equal cube root of x. And we want to differentiate that. We can't differentiate it how it is because we have the cube root sign basically. So we can rewrite that in terms using an indices law. So I'm going to just put it right here. Yep. So I'm going to say f of x is equal to the cube root of x. And this is the same thing as saying x to the 1/3. Why? Because basically the numerator right here, x to the 1/3, the numerator being 1 represents the power that x is raised to under the sign. And the denominator represents what kind of root it is. Cube root. So now that we have written it in terms of that, recall from the video, the part 1, differentiation part 1, the power rule. All we're doing is that we're going to copy and paste the power down. So we're going to copy and paste the 1/3 to be the coefficient of x. And then just subtract 1 from the power that we already have, the 1/3. So 1/3 minus 1 would simply give us minus 2/3. So that's what I'm going to have. And here we have our function differentiated. That's the first derivative. And with this, we can rewrite 1/3 x to the negative 2/3 in a simpler way. So let's work on doing that. So I just gave myself space. So here we have the first step, second step, and here's our third step. And we're just going to write this, the first derivative in a simpler way. So we have a third, 1/3 be multiplied by x to the 2/3. All right. So first thing I'm gonna do is that since this is being multiplied by 1/3, I could also write this as x over 3. So x to the minus 2/3/3. Since x is being raised to a negative power, I can have that in the denominator, x in the denominator basically. So I'm gonna have 1/3x 2/3. So notice how the negative is gone because I placed it in the denominator. Next is that since I have x being raised to the 2/3, I can rewrite this as 1/3 times the cube root of x squared. Because recall that the denominator represents right here, the third represents the type of root it is, and the numerator represents the power that x is raised to. And that is our first derivative of the function. So we move on to our fourth step, and that's simply to substitute x0 into what we have right here. So the value of x0 is 8. So I'm just going to substitute 8 into this. So I'm going to have, so this is step 4. I'm going to have 1/3 times the cube root of 8 squared. Now I'm going to just simplify. 8 squared is 64. So I'm going to have 3 times the cube root of 64. What is the cube root of 64? The cube root of 64 is simply 4. So we're going to have 1/3 times 4. 1/3 times 4 would give us 1/12. And yeah, that's the value of f prime of x0. Okay, so we know that f of 8, let me just write. We know that f of 8 is equal to 2, so that's what we're going to put there. Plus f prime of 8 is 1/12. So that's what we're going to have. And this is being multiplied by x minus 8. And from here, we're just going to simplify. So we'll have 1/12 being multiplied by what's in the brackets, x minus 8. So we're going to have 2 plus x over 12, because we're distributing, minus 8/12. We can simplify this. So we want to know what is 2 minus 8/12. So 2 minus 8/12, calculator, 4/3. So we're going to just have x over 12 plus 4/3. So this is telling us that with our original function, the cube root of x, we can basically, this function is approximately equal to x over 12 plus 4/3, and this is when x0, when x is close to x0. And yeah, and we are going to move on to the second part of the question. So we want to find what is the cube root of 8.05. And we want to find this using our first order estimates, being the equation that we just found. So that's what we're doing. So we have the cube root of 8.05, and this is approximately equal to the function that we just found, the first order estimate. So we're gonna have wherever we say x, we're gonna put 8.05. So this is 8.05 over 12 plus 4/3. I'm just gonna find what is the value of this. So I'm gonna put that in the calculator. So when we put it in the calculator, we're getting this number. So this right here is giving us 2.00416667. So now, in order to see if our first order estimate is true, is valid, we're gonna find what is the cube root of 8.05. So we're gonna use this expression. So cube root of 8.05. 5. So from here, this is what we're getting when we enter it. So right here, this is equal to 2.004158016. And if you notice, it's an estimation, it's an approximation. So you're gonna see that this, our original value, is close to our approximated value, because close to approximated, redundant, anyways. But yeah, they're close to each other, so our first order estimate is valid. So here's our second example. It says find the equation of linear approximation of the function f of x equal cos x at x equal pi by 2. And yeah, so it's the same thing, just like notice the kind of change in phrasing. So in the previous example, it said find the equation of the tangent, and in this example, it's telling us find the equation of the linear approximation. It's the same thing. Yeah, so with these questions, we're gonna highlight what we know, and they usually the question always give you the function as well as the point of the x, basically. So yeah, so we're gonna just put that in the general equation. So recall that the general equation is f of x, being the linear approximation function, is approximately equal to f of x naught plus f prime of x naught times x minus x naught. So with that being said, we're gonna have, since we know x is pi by 2, we're just gonna substitute it. So f of pi by 2 plus f prime of pi by 2. Yeah, since we know that x naught is pi by 2. Yeah. And this is being multiplied by x minus pi by 2. So from here, we know that we'll have to find what is f of pi by 2, f prime of pi by 2. And we're good. So yeah. So the second step is to substitute pi by 2 in the function, the given function. So what we're going to have is f of pi by 2 is equal to cos pi by 2. And when you're working with this, working with pi, radians basically, because pi by 2 is radians, you have to put your calculator in radians. So just remember that. So cos pi by 2 is the same thing as saying cos 90, and cos 90 is simply 0. So that's the value of f of pi by 2. So that would be 0. Next, we're going to differentiate the given function. So we're finding f prime. We want to know what is cos differentiated. So cos differentiated is simply minus sign. So that's what we're going to have, minus sign, and then just have the x. So since we know that, we're just going to substitute the pi by 2 into that to find what is f prime of pi by 2. So what is negative sine pi by 2? So sine pi by 2 is the same thing as saying sine 90. Sine 90 is 1. And since we have a negative sign there, we're just going to have negative 1. So this is equal to negative 1. And since we know these values, we're going to just substitute all of this in the equation. So here we're going to have, this is approximately equal to 0 plus minus 1 times x minus pi by 2, which would be approximately equal to minus, in bracket, x minus pi by 2. You can distribute the negative sign to have negative x plus pi by 2. Therefore, this function is our approximation. This is our first order estimate for the original function cos x. So this is our first order linear estimate. And what if we want to find cos pi? In fact, let me put this in bracket. My bad. Oop. Okay, what if we want to find cos pi by 2.003 using our first order estimate? All we're gonna do is just wherever we see x, we're going to put the pi by 2.003. So we're going to have cos pi by, let me just put it up here. So this is equal to negative pi by 2.003 plus pi by 2. And we're going to put that in the calculator. So we have a negative, oh, remember to put your calculator in radians. So we'll have a negative pi by 2.003 plus pi by 2. Okay, and this is the solution you're gonna get. So here, right here, over here, is equal to 0.00235 So now we just want to compare the values. So we're just gonna actually cos the pi by 2.003. And when we do that, so we're gonna have cos. So this is the value we're getting when we cos it. So let me write it down. We're gonna have 0.002352663. And notice the small difference. So here, the only difference we see right here is that it ends with a 3 and this ends with a 5. So the original value ends with a 3 and that's 5. So yeah, that's our first order estimate. So our next topic is higher derivatives. So all this time we're only thinking about the first derivative because we're only differentiating once. So all this time we have been finding the first derivative of whatever function. Higher derivatives is basically finding the second derivative, third derivative, fourth derivative, just not the first derivative. So you're basically differentiating over and over again. So if you want to find the second derivative, you're going to differentiate. If you have the original function, right, you're going to differentiate, find the first derivative, and then you're just going to differentiate the first derivative to find the second derivative. And the same steps apply with the third and fourth derivative. So notice right here, we have the notation. So for the second derivative, it's written as d squared y over dx squared, or f prime prime of x. So that's the second derivative, and we'll have the third derivative and the fourth derivative. So here we want to find the second derivative of the following functions. And the first one is f of x equal x squared minus x cubed minus x squared plus x minus 1. And yeah, so the first thing we have to do, we'll have to just differentiate normal, because yeah, we'll have to find the first derivative. And after finding the first derivative, we can get the second derivative by differentiating again. So right here we have variables being raised to a power. So we're just going to use the power rule. If you don't remember the rules of differentiation, you can go to my video, differentiation part 1, to remember them, recall the rules. So we're gonna find the first derivative, f prime of x, first derivative. So recall that all we're doing is that we're gonna copy and paste the power to be the coefficient of the variable. So we're gonna have 3x, and then we're just gonna subtract 1 from the power. So here, the x cubed differentiated would be 3x squared minus, we'll have x squared. So that's gonna give us 2x. We're gonna subtract 1 from the power. That's gonna leave us with 1, so we don't have to put it. And next we'll have x, which would simply give us 1. Because if we're supposed to actually differentiate it, x is the same thing as saying x to the first power. We're going to copy and paste the power to be the coefficient. So we're going to have 1x and subtract 1 from the power. So 1 minus 1, that leaves us with 0. Any number raised to anything raised to 0 gives us 1. So that's what we'll have. And of course, the constant is going to be 0. And yeah, that's our first derivative. To find the second derivative, we'll have to differentiate again. So we want to find f prime prime of x. So we're going to follow the same steps, the power rule. So we have 3x squared. Copy and paste the power to be the coefficient of the 3x. So we're just going to multiply the 2 that we bring down by the 3. And when we multiply 2 and 3, we're going to get 6. I'm going to subtract 1 from the power. 2 minus 1 is 1, so we're simply left with 6x. Next, we'll have minus 2x. So that's going to give us 2, minus 2. And of course, the constant becomes 0, so we don't have to put it. And yeah, that is our second derivative. So this will be the answer. The second derivative of the function up here is 6x minus 2. So now we move on to our second example. We'll have y equals sine of 2x cubed minus 9x. And when we're differentiating this, rewatch the video, rewatch differentiation part 1. All we do is that we're going to have this, the function that we have right here, we're going to differentiate it and make it the coefficient of the expression. Then we're going to differentiate the ratio, the trig ratio, and then leave the function as it is. So that's what we're going to do. So we want to find the first derivative first in order to differentiate that and find the second derivative. So we're going to have dy by dx is equal to, so here we have 2x cubed minus 9x. So that differentiated would be 6 x squared minus 9. So that would become the coefficient. We differentiate the ratio, the trig ratio. Sine differentiated would give us cos. And then we're going to have the function in the brackets as it is. And yeah, that's our first derivative. In order to find our second derivative, we'll have to differentiate that. So the same steps apply. You're going to differentiate what's in the function, what's in the brackets already, the function right here. And we know that this differentiated would simply give us this. So when we differentiate it and it becomes the coefficient of this, basically, we're going to multiply what we have right here times this, basically. So just like how we said that this differentiated, the what's in bracket differentiated is 6x squared minus 9. If we're supposed to differentiate it right here, it's going to give us the same thing. So I can just write 6x squared minus 9 squared. Because at the end of the day, when I differentiate this and it becomes a coefficient, I have to multiply it by the coefficient that's already there. And 6x squared minus 9 times 6x squared minus 9 is simply 6x squared minus 9 squared. Yeah, next you're going to differentiate the ratio. So cos differentiated would give us sine, negative sine. So what I can do, I'm going to put the negative right here. And then I'm going to write sine. And then remember that this remains the same. And yeah, that's our second derivative of the function. And here we have our third example. So we'll have y is equal to e raised to the negative 5x plus 8 ln 2x to the fourth. So right here, we'll have an exponential function. And in order to differentiate that, remember we're finding the first derivative first. Okay. In order to differentiate the exponential function right here, we're going to differentiate the power, the exponent, make that the coefficient, and just leave the function as it is. So we'll have negative 5x. That differentiated would simply give us negative 5, and then we're just going to have the same thing again. Next, we'll have a ln, a log function. So I'm going to just write back the coefficient. We'll have a log function. And with this is basically telling us is that what we have in the bracket right here, the 2x to the fourth, in fact, let me write it. Okay. So all we're seeing is that ln differentiated would simply be represented as the what's in the bracket differentiated being the numerator, and then the original what's in the brackets being the denominator. So what we're gonna do, we're gonna just put all of this in bracket because remember we'll have an 8 right here. So I'm gonna differentiate what's in the bracket. So 2x to the fourth differentiated would simply give me 8x to the third, and then I'm just gonna have what I have in the bracket as the denominator. And of course I can simplify that. So I'm gonna rewrite this to have this would cancel out, not cancel out, I can break it down. So 8 divided by 2 gives me 4. And then I have 8 times 4, that's give me 32. And then since I have x raised to the 3 in the numerator and x raised to the 4 in the denominator, that simplified would simply be x raised to the negative 1. And yeah, that's the first derivative. Remember that we're finding the second derivative. So we're finding d squared y over dx squared. So we're just going to follow the same steps. So this, we're going to differentiate the power. And of course, we know that that differentiated would give us negative 5. So all we're saying is that negative 5 times negative 5 will give us 25. Because in fact, I'm writing. So I'm going to have negative 5 and negative 5. And then leave the function as it is. Because we're following the same steps. You're just differentiating again. Next, we'll have 32x raised to the negative 1. So we're going to just bring down the negative 1. We're going to copy and paste the power. So we're going to have 32 times negative 1. And then we're going to subtract 1 from the current power. So negative 1 minus negative 1 minus 1 would give us negative 2. And we're going to simplify. So we'll have negative 5 times negative 5. That would give us 25 of e raised to the 5x plus we'll have 32 times negative 1. So that gives us negative 32 and x raised to the negative 2. And I can write this in a different way to say that this is 25 over e to the 5x because we have a negative plus, in fact, let me not put plus because we have a negative sign. So I'm going to say minus 32 over x squared. We move on to the concavity of a curve. So with this, we're just describing the graph, whether the graph curves upwards or it curves downwards. If the graph curves upwards, we'll call it a concave up. If the graph curves downwards, we'll call it a concave down. And in order to test for the concavity of a curve, basically, we use the second derivative. So if the if the graph curves upwards, meaning that it's a concave up, the second derivative would be greater than 0. However, if the graph curves downwards, meaning that it's a concave down, the second derivative is less than 0. Our next concept is point of inflection. So with this, it basically describes the point where there's a change in concavity. And this is basically for continuous functions where there's a concave up and a concave down, like what we see right here. So right here, you notice that there's a concave down and then it changes to a concave up. In between the concave down and the concave up, there's a point where it basically changes. And we call this the point of inflection. And all we're saying is that with this point, in order to determine the point of inflection, the second derivative, we're just going to equate the second derivative of the function to 0. So here we have a stationary point. So the stationary points are just the point where the first derivative is equal to 0. And when we're classifying the stationary points, we're thinking of whether the point is a minimum point or a maximum point. And what we use to classify stationary points is the second derivative. So if it's a minimum point, we would have that the second derivative is greater than 0. However, if it's a maximum, the second derivative would be less than 0. And yeah, that's basically it for stationary points. Down here, we'll have increasing and decreasing functions. So if you look at the little diagram right here, the function right here, we have this continuous function, right? And we're seeing that once we go up the curve, basically, it's increasing. However, when we go down, it's decreasing. And the point in between the place where it increased and decreased is the stationary point. So the stationary point is the turning point, basically. And yeah, so when the function, if to determine if the function is increasing, we'd use the first derivative, and the first derivative should be greater than 0. So if the function is increasing, the first derivative is greater than 0. However, if it's decreasing, the first derivative is less than 0. So here we have our example. This is going to be a 4-part question. So I'm doing the first 2 parts now. Yeah. So here we have a function f of x equal x cubed minus 3x squared plus 2, and we want to find the stationary points of the function and their coordinates, as well as we want to classify each stationary point. So recall that in order to find the stationary point, we're saying that the first derivative of the function is equal to 0. So we have to find what is the first derivative. So with this, we're going to have, let's rewrite our function, f of x equal x cubed minus 3x squared plus 2. So our first derivative would be equal to, so x cubed differentiated would be 3x squared, and then we're going to have minus 6x, and that's our first derivative. We're saying that the stationary point is when the first derivative is equal to 0. So all we're going to do, we're going to equate this to 0. So we're going to have 3x squared minus 6 equals 0. Notice that this is a quadratic. However, in this case, we can just factor normal. So we have 3x squared minus 6x squared. We're looking for a common factor. Our common factor in this case would simply be 3x. And that would leave us, in brackets, x minus 2. And that would be equal to 0. Therefore, in this case, we would have either 3x is equal to 0 or x minus 2 is equal to 0. So if this is equal to 0, therefore x would be equal to 0. And if x minus 2 is equal to 0, we would have x is equal to 2. And that is simply our x values. However, remember that the question asks for the coordinates. So remember it's a point. So if you're thinking about a point, you have to think of the x coordinates as well as the y coordinates. So in order to find, we'll have our x coordinates right here. In order to find the y coordinates, all we're doing is that we're going to substitute our x values in the original function. So we have x is equal to 0. I'm just going to go up here. Sorry to be confusing, guys. Right here. I'm going to go up here. So we have x is equal to 0. If we're supposed to substitute 0 in the function, so we'd have 0 cubed. That will give us 0 minus 3, 0 squared. That will give us 0 as well, plus 2. So when x is equal to 0, y would be equal to 2. And for when x is equal to 2, just going to substitute, same thing. So when we substitute 2 in the original function, we're going to have 2 cubed. 2 cubed is 8. So I'll just make a note up here. Minus 3, 2 squared. 2 squared would give us 4. And 4 times negative 3 would give us minus 12. Plus 2. When we simplify that, we're going to get negative 2. So we'll have 8 minus 12. 8 minus 12 is negative 4. Negative 4 plus 2. Negative 4 plus 2 would give us negative 2. So y would be equal to negative 2. Therefore, our coordinates would simply be 0, 2, and 2, negative 2. And that's it. And now we want to classify each stationary point. So we want to find out if it's a minimum or a maximum. So recall that if the stationary point, if the second derivative is greater than 0, it's a minimum stationary point. If the second derivative is less than 0, it's a maximum stationary point. So all we're going to do, since we have our first derivative, we're just going to differentiate this to get the second derivative. So f prime prime of x is equal to, so we have 3x squared. 3x squared would give us 6x differentiated minus 6. So that's our second derivative. So now that we have our second derivative, in order to find out if our stationary points are minimum or maximum, we're just going to substitute. So we're going to start with the x equals 0. So we're going to have 6 times 0 minus 6. And that's going to give us negative 6. Since negative 6 is less than 0, that would therefore mean that our point right here, the coordinate 0, 2, is a maximum. So I'm just gonna write max. That's our maximum point. And for the second point, we're gonna substitute the 2 into this. So we're gonna have 6 times 2 minus 6. 6 times 2 is 12, minus 6 gives us 6. Since 6 is greater than 0, that would mean that our coordinate right here, the 2 and negative 2, is a minimum point. And that's how we classify stationary points. So let's just go over everything. Remember that a stationary point is simply the point where the first derivative is equal to 0. So all we did, we have our function, we differentiated it to get the first derivative. And after differentiating it, we equate it to 0. When we equate it to 0, we basically solve for x. And when we did that, we get x is equal to 0 and x is equal to 2. Remember that it's a point, therefore you have to consider the y coordinates. In order to get the y coordinates, all you do, you substitute the x values in the original function. And when we did that, we got that when x is equal to 0, y is equal to 2, giving us the coordinates 0, 2. And when x is equal to 2, y is equal to minus 2, giving us the coordinates 2, minus 2. And in order to go down here and classify each stationary point, you basically have to use the second derivative. So recall that if the second derivative is less than 0, when we substitute the x value, it's going to be a maximum point. If the second derivative is greater than 0, when we substitute the x value, we're going to get a minimum point. So that's the classification. So right here, we substituted 0, x equals 0 in this, and we got negative 6. Since negative 6 is less than 0, that would make the coordinate 0, 2 a maximum point. And then right here, we did the same thing. We just substitute the 2 into the second derivative function, basically. And when we did that, we got 6. 6 is greater than 0. Since 6 is greater than 0, that would mean that 2 and negative, the coordinate 2 and negative 2 is a minimum point. So here we have the third part of the question where we want to find the intervals where the function is increasing and decreasing. And recall for increasing and decreasing functions, we use the first derivative. So here we're gonna have that for the increasing, we're gonna have that the first derivative being the 3x squared minus 6x is greater than 0 for the increasing. We're gonna just factor out normal. We'll have a quadratic inequality. So just factor normal where we have that, because we did that in the first part of the question. And for the critical points, being the points where x is equal to some value, we know that it is x is equal to 0 or x is equal to 2, because recall from the first part of the question. So from here, since we know the critical points, in order to basically determine the interval, we can use a graphical method. So we're gonna have 0 and we're gonna have 2. Oh, I should have drawn the curve first. And notice how I draw the curve like this, because I'm looking at the coefficient of the squared term right here. So since the coefficient of the squared term is positive, is 3, it's positive, we're gonna have a minimum curve. And a minimum curve is when it's basically like a smile. And then we'll call that the maximum point, the maximum curve. If it's a maximum curve, that means that the square term is negative. So it's gonna be like a frown. Yeah, from here, since we're seeing that we have our minimum curve, and we're seeing that this is our function. This is our function, 3x squared minus 6x. We're saying that this is greater than 0. Therefore, I'll just have the x-axis right here. We know that above, not the x-axis, the y-axis. We know that above the x-axis, the y-axis is positive, and below the x-axis, the y-axis is negative. Since we're considering the function being greater than 0, we're looking up here. So we're considering values up here. all the way up here. So we're ignoring this part because that's less than 0, negative. So with that being said, since up here, we're looking at up here, we can basically determine the interval. So from looking here, since we're looking at the top, we can see that x is less than 0 or x is greater than 2. X is greater than 2. And that would be our increasing function. So x, hope you can see properly. I feel like it's not written properly. So x is less than 0 or x is greater than 2 for our increasing function. Now, if we want to find the decreasing function, all we have to do is just take the opposite of this. So since we know that when the function is increasing, the intervals would be x is less than 0 or x is greater than 2, meaning that this is disjoint. If we want to consider the increasing function, that means that it would be the complete opposite of this. So since this is disjoint, this would become joint and would have the opposite. So we'll have x is less than 0. Since x is less than 0 for the increasing, we're going to have x is greater than 0. And then we have or x is greater than 2. Therefore, we're going to say x is less than 2 for the decreasing function. So yeah, so here we have the increasing function interval being x is less than 0 or x is greater than 2. And for the decreasing function interval, we have x is greater than 0 and x is less than 2. Disjoint, joint. And here's our final part and also the final question for this video. So here we have the intervals. We want to find the intervals for concavity and the points of inflection. So recall that for concavity, when we're testing for concavity, we're using the second derivative. And if it's a concave up, that means that the second derivative is greater than 0. If it's a concave down, the second derivative is less than 0. So here we have our second derivative. So we're gonna have for concave up, I'll just write it, concave up. We're gonna have 6x minus 6 is greater than 0. And we're just gonna solve this inequality normal. So we're gonna have 6x is greater than 6 because we're adding 6 on both sides. And then when we divide by 6 right here, we're gonna have x is greater than 1. And that's for the concave up. For the concave down, we're gonna have 6x, the second derivative, is less than 0. And we're just gonna solve this normally. So 6x is less than 6, x is less than 1. And that's for the concave down. And then it asks to find the point of inflection. Recall that the point of inflection is simply where there's the point where there's a change in concavity. And it simply means that the second derivative will be equal to 0. So we're just solving for that. So we're gonna have for the point of inflection. Kind of right, bud. Anyways, we're gonna have 6x is 6x minus 6 is equal to 0. 6x is equal to 6. X is equal to 1. Because, yeah, expected. But yeah, so this is for the concavity. We use the second derivative. If it's a concave up, the second derivative is greater than 0. If it's a concave down, the second derivative is less than 0. In order to find the point of inflection, it simply means that the second derivative is equal to 0. That's all, guys.